Hello, this physics video is on the field of a dipole. We are finishing up chapter 21 on electric fields and electric charges in Young and Freedman's University Physics. And this section, final section of the chapter, is on electric dipoles. I've done one video already on this section on the force and torque on a dipole. But the chapter ends with this section on the field generated by a dipole. So we want to ask, what about the electric field generated by a dipole, not on a dipole, but not the field on a dipole, but the field generated by a dipole. And we know a couple things already, right? We know that at any particular point, the total electric field, E vector, is going to be the vector sum of the fields from those two charges. So for example, if we want to know what's the field created by those two charges, it's going to be the vector sum of those fields at any particular point using the principle of superposition. The principle of superposition says that fields don't interfere with each other. We just say, well, the field from this point is this, and the field from this point is this, and therefore the vector sum of those is the field here or here or here or here or here. And so this can be a little complicated as it seems, and you have to figure it out with regard to here, and you have to figure it out with regard to here. And so they have little choice but to give us an example. So this is kind of a lot of clutter. So let me explain what's going on with this example that they use to give us just a window into the complexity. Computers sometimes have to be involved to come up with these things. But to give you a little bit, or at least otherwise it would take us a very long time. But so let's consider the electric field at a point P. I should have put a P, but let's say at point P, and they're going to make it very simple. So here's the x-axis, here's the y-axis. So the point P is on the y-axis, and the dipole, which are two charges of equal and opposite magnitude, are down here, equidistant from the origin. Okay, so they've made it very simple. The charges in the point are all on the y-axis, and the charges are equidistant from the origin, making it very simple. And we're going to ask, what is the electric field created by this dipole at some point P? Maybe far away, from them. And if these are d apart, then we know that this is d divided by 2. The negative charge is d divided by 2 in the negative y direction. And the positive charge is d divided by 2 in the positive direction, okay? And this is supposed to be a p here. That's the dipole moment, which goes from negative to positive, is going in this direction. And you'll remember that the dipole moment is qd, the charge times the distance, but that won't come in until the very end of the video. But so we can say that from point P and the negative dipole, what is the distance from point P and the negative dipole, negative charge of the dipole? Well, it's going to be y plus this d divided by 2, and that's the distance. Y plus d divided by 2 is the distance from the point to the negative charge of the dipole. What's the distance from that point to the positive charge? Well, it's going to be y minus d divided by 2. Okay, so that's where these come from. The distance from the point to the negative charge is y plus d over 2, and the distance from point P to the positive one is y minus d over 2. Okay, so this is the situation that we have set up. It's a fairly easy situation as such situations go. Okay, now here's the charge. This is the formula for electric field that we learned earlier in the chapter. The electric field is this constant, 1 over 4 pi epsilon naught, times the charge divided by the distance squared. Okay, we know that. So in this particular case, we can plug in the numbers. So this is the distance from the positive charge, and this is the distance from the, or I'm sorry, not distance. This is the part that has to do with the positive charge, and this is the part that has to do with the negative charge. Okay, and the positive charge is pushing positive, and the negative charge is pulling toward it. And so that's why we have the negative with the negative charge, because it's pulling in the negative y direction, as opposed to the positive charge, which is pushing in the positive y direction. Okay, so both of these had a q, right? q over r squared for the positive charge and q over r squared for the negative charge. We factored out the q because both of them had a q. We factored out this constant there. And so that's the 1 is left because we factored out the q. And then this is basically r squared down here. Remember, we said that from the positive charge, remember, from the positive charge, this was the distance, and this was the distance for the negative charge. And so there you have it. We're going to square r squared, and then here is r squared for the negative charge. Okay, great. So now we do a little bit of algebra. Now what they've done is they have multiplied this whole thing by y squared over y squared. Well, y squared over y squared is, believe it or not, 1, right? Anything divided by itself is 1. And so the y squared over y squared, there's the over y squared. And so when you have y squared in the top, I double checked the math here. I multiplied them out just to make sure that Young and Freedman weren't cheating here. I didn't put it in the PowerPoint, but basically, if you multiply this out using the FOIL method, first, outside, inside, last, y squared minus 2 dy divided by 2, plus d squared over 4. I went ahead, I put it all out, I divided it by y squared, and yes, indeed, this is true. This is what this works. And so just, we can trust Young and Freedman that the algebra works. And so this is an equivalent form of this. We've just done a little bit of hokey pokey. So the binomial theorem. The binomial theorem basically says that if we have 1 plus x raised to the n power, then we can expand that out, for however many. So the first is going to be 1, then nx, and basically the way you get the coefficient is this horrible looking thing, n factorial over k factorial times n minus k factorial. N is the power, k is the number in order. So like this is 0, this is 1, this is 2, then there'd be a 3 and 4 and 5 and 6. So k is which one we're on, so this gives us the coefficient for whichever one we're on. Now, so let me go back here and say that here we have 1. This is to the negative second power, right? So that our power n equals -2 in this particular case, and then we have 1 plus something. Okay, and so this is the x right here. This is the x, and so we can use the binomial theorem to expand this out. Now this is where it gets complicated, because I mean they've started with something that's fairly low on the totem pole here, fairly simple. By the way, factorial is like the factorial of 4 is 4 times 3 times 2 times 1. That's how factorials work. And by definition, 0 factorial is 1. And so if you're a little thrown off by, wait a minute, this is the 0th term, isn't this going to be something divided by 0? Well, by definition, 0 factorial is 1. So k factorial, when k is in the 0th position, it ends up being 1. So basically, this is the way it ends up. Now, what Young and Freedman tell us is that as we get to higher numbers of k, excuse me, not higher numbers of k, but when y is far away from the dipole. So when we're talking about a situation where we're asking where's the electric field and it's considerably farther away, far away from the dipole, then basically the y becomes much bigger than the d, and this becomes 0. And so when we get to terms far away, they become more or less 0. And so they don't do a precise expansion. They just drop off past the first two terms here. So the first term, so if we take this, this is what we ended up, right? This is where we ended up with this. So if we take that, and we put in -2 for n, and negative d over 2y for x, and we go ahead and plug it in, what we're going to get is 1 plus d over y for this second term. Because remember, nx is the second term, -2 is n, and x is negative d over 2y. So the 2's are going to cancel out, and the negatives are going to cancel out, and we're going to be left with d over y. So this approximately in the situation that we've set out is 1 plus d over y. Now that is if you remember from, again, reminding you, this was the first bit. Now what about the second bit? Well, let's do the second bit. If we do the same thing with the second bit, we end up with the same thing, but here the -2, the 2's cancel out, but it's negative times a positive, which is a negative. So this is what we end up with in terms of the binomial expansion. When we plug in the particulars of this situation to this situation, this is going to become, what was it, 1 minus d over y, and this is going to become 1 plus d over y, or vice versa. Actually, it's vice versa. Okay, so now we can go back to the original, and we can take that E, the electric field at that point, is going to be all this times this, using the binomial expansion. This is what we've ended up with. Well, you see 1 minus 1, that's going to disappear. And then negative and negative positive, so we're going to end up with 2d over y. And so the 2 and the 4 are going to cancel. We're going to end up with 1/2. The d becomes qd, which is also the dipole moment, right? We just said that. And the y at the bottom is going to become y cubed here at the bottom. So therefore, the electric field at that point, if y is at some distance, is going to be the dipole moment divided by twice pi epsilon naught times the distance y cubed. So actually what we find out here is that electric fields from dipoles in any direction decrease, in proportion to the distance cubed, which is interesting. And then as a final kind of note in this section, they note, Young and Freedman note that it turns out that quadrupoles, this is dipoles, four charges in equidistance from each other, quadrupoles actually decrease proportional to the distance away from them to the 4th power. So anyway, this has been a little taste of how complicated it can be with electric dipoles in terms of the force that they generate. And this has been the end of chapter 21 on electric fields and charges. On to Gauss's law.